Question 1 from the 2012 Level 1 Mechanics paper. A woman drives a tractor down a sandy beach to pick up a friend's boat. The distance time graph below shows part of the journey, and you can see initially there's a small upward curve for the first 30 seconds and then it's straight for the next 60 seconds. Use information from the graph to calculate the average speed. The average speed is the total distance, which in this case is 600, over the total time, which is 90. So 600 over 90 it gives you 6.666666, or around at 6.67 meters per second. So that's A. Part B. Describe the motion of the tractor in section B and explain what this tells us about the force acting on the tractor during this time. Okay, let's go back up to there. During section B, we can see that it's a constant change in distance over change in time. So constant change in distance over change in time comes from that velocity formula, distance over time, or change in distance over change in time, which means there is a constant change in distance over time, so there's a constant velocity. So we would write there's a constant velocity. Okay, constant velocity, or constant speed. So that describes the motion. Explain what this tells us about the force. That means the forces are balanced, so there's an equal amount of thrust and friction. You could also describe it as the net force being 0 newtons. C. The total mass of the tractor and driver is 1,660 kilograms. Calculate the speed of the tractor at the end of section A, and then calculate calculate the net force acting on the tractor during section A of the graph. Okay, this is a little bit convoluted, so it's best just to take it step at a time. So the first thing, calculate the speed of the tractor at the end of section A. If we go up, have a look at our graph. At the end of section A is this point right here. So there's section A. So at this point here, the speed stops changing, and it's constant. So it's constant through the whole length of section B, which means we can use the gradient of section B, the rise over the run, to find what the speed is at the end of section A. Now we can't just use the 6.67 from here, because that's the average speed over the entire journey. And that would be like, excuse me for my graph getting even more mixed up, that would be like us taking a point here and a point at 0, 0 and drawing a line there. And that'll give us the average speed if it was going at a constant speed all the way through. So we can't do that because it's increased a bit and then it's gone constant for along here. So we need to know the final speed at this point, which is the slope of the graph. So we would do 600 minus 120. So I'm just going to write it up here, minus 120, so that we're not missing the graph while we're trying to do the bit. And over the time, 90 minus 30. So that gives us the true rise over the run for that section of the graph there. Okay, getting very messy. And if you do that calculation, you get, let's have a look. Okay, it's on the marking schedule somewhere, which you can't see right now, but anyway, that'll give you a speed. Let's carry on going down. So that'll give you the final speed, I'll just call it VF, at the end of A. Okay, so gradient of the graph, here's our little reminder. Not that bit, that bit. So the gradient of that part here. So the second point is calculate the net force. So let's look at this. F equals ma. That's our standard force equation, Newton's second law. We know the mass. We're trying to find the force, and perhaps we can calculate the acceleration. Remember, the acceleration is the change in speed over the change in time. We know it started at 0 velocity, 0 meters per second, and it went up to whatever we calculated from the gradient of that second part of the graph. So we can calculate that. We've got 0 to that final velocity at the end of A, gives us this bit. We know the time was 30 seconds from 0 to the end of section A, so we can calculate A. That means we can substitute A into there and rearrange, well, not even rearrange, just calculate the force. Okay, I'm not going to use the numbers because it gets a bit unwieldy on this thing. D, well, on a sandy beach, the woman sees a car that is stuck in the sand. The car, if I'm taking note of that, the mass of the car is less than the mass of the tractor. Photos below show the tread patterns of the tractor. There's a tractor and the car's tyres. Compare the different treads of the tractor tyre and car tyre in terms of force. Okay, we're comparing the force, we're comparing the surface area, and we're comparing the pressure. And then we're using this comparison to explain why the car gets stuck in the sand but the tractor does not. Okay, so it's good to highlight or to make bullet points out of a question if they're not given to you. They sometimes make it a little bit harder by not giving you the bullet points, but in any case, comparing the treads in terms of force, let's do it this way. We've got the car and we've got the tractor, and we're looking at the force, and the car is less and the tractor is more because there is more mass for the tractor, so it will have more downward force. And remember, force, surface area and pressure, we're ultimately looking at our pressure equation, which is force over surface area. So we've done force, surface area. Surface area, you could just use A, but I'm using SA. The car has more surface area because it's got quite a flat looking tread. The tractor has less surface area because it's got these high ridges here, which are where the surface area of the force is applied over. So when we get right down to it and we're looking at the pressure, if we use the pressure equation, force being less for the car divided by a greater number for the surface area, the car is definitely going to have less pressure. For the tractor, you've got more force over the low surface area, so it's going to have a higher or a more pressure. And then, so that deals with surface area and pressure. And the final comparison to explain why the car gets stuck in the sand but the tractor does not. It's a little bit misleading to say it gets stuck in the sand. It's actually better to say it can't grip the sand. The tractor does not get stuck in the sand because it grips the sand. Because the treads with higher pressure will sink into the sand and grip the sand more. Whereas the car will have not enough pressure to sink into the sand and will just slide over the surface without gripping anything. And there you go. That's all.